Today we're going to study the convergence of a pretty interesting series. So it'll be the sum as n goes from 1 to infinity of 1 over n to the power 1 plus the absolute value of sine of n. And what makes this series interesting? Well, I think it's sort of like in the flavor of the following two series. And so we know that for all epsilon bigger than 0, if we have 1 over into the 1 plus epsilon, then that series will converge. And that's by the p-series test. But that's for a fixed epsilon bigger than 0. Whereas if we've got something like this, so the sum as n goes from 1 to infinity of 1 over n to the power 1 plus 1 over n, that in fact diverges. And so of course, here we're adding something to the number 1, and we're adding something that depends on a variable. So this case doesn't apply. And before we get started, I'd like to mention that this was problem 11162 from the American Mathematical Monthly, and we're following the solution from that publication. Okay, so let's start by defining the following two indexed sets. So the first set we'll call A sub n, and it'll look like this. So the general shape of an element will be an integer. So we've got all integers m, and they have to satisfy a couple of rules. So first of all, they have to be bigger than or equal to 0 and less than or equal to 2 to the n minus 1. And that minus 1 is outside of the exponent. And they also have to satisfy the rule that if you plug these numbers into the sine function and take the absolute value, you get something that's less than 1 over n. Of course, it makes sense that we would want to have it less than 1 over n, just in the spirit of this thing over here. So that'll be my first family of sets. And then my second family of sets, well, they're in fact just subsets of an, and we'll call them bn. And what they are, well, they're going to be an intersected with the following subset of integers. So it'll be 2 to the n minus 1, and then 2 to the n minus 1 plus 1, all the way up to 2 to the n minus 1. So it's like the top end of numbers that would satisfy this rule right here. Okay, so let's look at some examples of these sets just to get a feel for what they look like. So let's look at A sub 1. So A sub 1 works out to be just the numbers 0 and 1. And well, why is that? Well, this is actually a list of all the numbers satisfying this rule for n equals 1. But then sine of 0 is 0, and sine of 1, well, it's less than 1 in absolute value, so it satisfies that rule. And then likewise, we can notice that B sub n is just the singleton 1. Now let's look at A sub 2. So let's start off by noticing that that's all numbers between 0 and 3. So in other words, it's 0, 1, 2, and 3. And then when you plug them into the sine function, you have to get something less than a half. And so if you look at those, you'll see that you get the number 0 and the number 3. Those are the only things that satisfy those two conditions. And then you look at B sub 1, and you'll see that you just get the singleton 1. And now let's move down. So let's look at A sub 2. So that's going to be all numbers between 0 and 4 minus 1, or in other words, 0 and 3. And then when we plug them into the sine function and take the absolute value, it must be less than 1/2. So in fact, what you get here are the numbers 0 and 3. So it turns out that sine of 1 is larger than a half, and sine of 2 is also larger than a half, at least if you take the absolute value. And then B sub 2, just taking the appropriate intersection, is the singleton 3 here. Okay, so let's maybe do one more. So A sub 3. So that'll be all the numbers from 0 to 7, so that when we plug them into the sine function and take the absolute value, it's less than 1/3. So this turns out to be 0, 3, 4, 5, and 6. And then if you look at B sub 3, it's going to be everything that is bigger than or equal to 4 from the definition of B sub n. So that'll simply leave us with 4, 5, and 6. And now let's observe a general rule that kind of ties this family of sets together. So let's write it down here. So let's notice that we have a sub n must be a subset of a sub n minus 1 disjoint union with b sub n. And so let's talk our way through this. We'll notice that the b sub n capture all of the members of a sub n after a certain point. And then a sub n minus 1 accounts for all of the ones earlier than that. But we get this subset rule here because the inequality restriction is weaker for a sub n minus 1. Okay, so anyway, we've got this rule right here binding together these two types of sets. Okay, well, what does this say about the size of these sets? Well, that means that the cardinality of a sub n is in fact less than or equal to the cardinality of a n minus 1 plus the cardinality of bn. And while let's like underscore here that we had a disjoint union, so taking the cardinality of a disjoint union, you truly get the sum there. Okay, but then we can solve for b sub n, and we'll see that in fact the cardinality of b sub n is bigger than or equal to the cardinality of a sub n minus the cardinality of a sub n minus 1. So we've got this like nice result having to do with the size of these sets. Now let's see what we can do with that. Now here comes a really interesting part of this argument, and this is to estimate the size of a sub n. So we'll start with the unit circle within the complex plane. So this is the unit circle within the complex plane. And then we're going to partition this unit circle into 7n equal arcs. So let's maybe do that here. So that makes a little bit of a wedge here, and maybe like a wedge there, and a wedge there, and then we'll keep going around over and over and over. But we're getting 7n total of these. But since we're getting 7n total of these, we know exactly like how big this angle is. And this angle is 2 pi over 7. Okay, nice. But then we can go over here and we know exactly what this point is in the complex plane because the complex exponential parameterizes the unit circle so nicely. And this is the point e to the I times 2 pi over 7. Whereas this over here would be e to the I times 4 pi over 7n. I guess I should say 7n there because our angle is 2 pi over 7n. And then next up, let's take the following types of numbers. So they'll be of the form e to the I k, and then k is going to come from the following set. So it'll be the set containing 0, 1, 2, ending at 2 to the n minus 1. And so look, that's pretty similar to what's going on with our definition of a sub n. We're just putting it into the exponent of this complex exponential here. And now let's notice by the pigeonhole principle, there'll be one of these 7n arcs that contains, well, a certain number of these. And what number is that? Well, it's the number of elements in this set divided by 7n. So let's maybe write that down. So there is an arc with greater than 2 to the n over 7n of these e to the ik. Again, like I said, by the pigeonhole principle. Another thing maybe to notice like pretty quickly is that this 2 to the n over 7 times n is in fact bigger than 2 when n is bigger than or equal to 7. So we'll make use of that at some point as well. Now let's enumerate these k's that end up in the same part of the arc, or their complex exponential ends up in the same part of the arc. And we're going to do it in like decreasing order. So we'll have 2 to the n is bigger than k sub m, which is bigger than k sub m minus 1, all the way down k sub 2, which is bigger than k sub 1, which is bigger than or equal to 0. And, you know, by our observation right here, what do we know? We know that this number m is bigger than 2 to the n over 7 times n. Okay, so now we've made this geometric argument, so now let's like kind of summarize that and see where that takes us. So here's a summary of what we did on the last board. So we found m total numbers that were between 0 and 2 to the n, and I've put them, I think, in a slightly different order, but this is a little bit easier to work with. And by the pigeonhole principle, we knew that m was bigger than or equal to 2 to the n over 7n, and these satisfied the following rule, that e to the I kj, where j is between 1 and m, are in the same portion of an arc on the unit circle where the angle was 2 pi over 7n. So recall that was by splitting up this unit circle into 7n equal arcs. Okay, so now let's suppose that n is bigger than or equal to 7, and then after that, let's take k1 and then kj with maybe j between 2 and m. Okay, nice. And we're guaranteed to be able to take 2 of them because if n is bigger than or equal to 7, then by this rule right here, we know that m is bigger than or equal to 2. So we definitely can get 2 of them. Okay, so now let's notice this business about being in the same portion of an arc with a certain angle is the same thing as saying that the modulus of e to the I k1 minus e to the I kj is less than or equal to 2 pi over 7n. But now you might say, well, where did this 7n thing come from? Well, it came from the fact that pi is less than 3.5, so 2 times pi is in fact less than 7. So that means that we can pin this above by 1 over n. Okay, so that's good to see. Now let's maybe extend this inequality out. So I'm going to put the 1 over n way down here, and then I'm going to factor out an e to the I kj. So that'll give me a modulus of e to the I kj, and then we multiply that to e to the I k1 minus kj minus the number 1. But now e to the I kj is simply equal to 1, or after we take the modulus it's equal to 1, because that's on the unit circle. But then we can also rewrite this bit right here using Euler's formula for the complex exponential. And that'll look something like this. So we get cosine of k1 minus kj minus 1 plus I times sine of k1 minus kj. And that's like strict equality there. But notice that if we take the modulus of a complex number, we're going to get something that is necessarily bigger than or equal to just taking the modulus of either the real part by itself or the imaginary part by itself. And so we might as well just drop this off and take the modulus of the imaginary part. And so that would be simply the absolute value of the sine of k1 minus kj. So that brings us down to the following inequality. So we have absolute value sine of k1 minus kj is in fact less than 1 over n. Oh, but check it out. By our construction, since k1 is bigger than k2 and so on and so forth, and they're all between 0 and 2 to the n, that means that k1 minus kj is, well, in the size requirement to get inside of an. Oh, but since we've put it below 1 over n, it satisfies this rule to get inside of an as well. So that means we've just found a lot of elements of an. So for example, k1 minus k1 is inside of an, in other words, the number 0. And then so is k1 minus k2, k1 minus k3, all the way up to k1 minus km. And that's just by indexing those j's through. So, like I said, these are all inside of a sub n. But what does that tell us? That tells us that the size of a sub n is at least m, because we found m elements right here. But our m is bigger than or equal to that 2 to the n over 7 times n. So there we've done it. We found some sort of estimate for the size of a sub n. Now let's see how we can use that. So here's some relevant data from the last board. We know for n bigger than or equal to 7, the size of a sub n is bigger than or equal to 2 to the n over 7n. Now we're ready to make the final type of calculation. So let's start over here. We've got the sum as n goes from 1 to infinity of 1 over n to the power 1 plus absolute value of sine of n. Well, that's going to be equal to the limit as capital N goes to infinity of the partial sum. So that'll be the sum as n goes from 1 to capital N of, well, the same thing. So we've got 1 over n to the 1 plus sine of n, and that's inside of absolute values. And now we're going to start using our inequality. So let's first of all bring out the sixth partial sum, and then we can use our result for this n bigger than or equal to 7. So this is going to be equal to the sixth partial sum plus the limit as capital N goes to infinity of the sum as little n goes from 7 up to capital N, and then we're going to introduce an inner sum here, and that's going to be between powers of 2. So this will be k going from 2 to the n minus 1 up to 2 to the n minus 1. One of those is in the exponent and one isn't. And now we'll have the same argument for our sum. So that's just kind of indexing these things between powers of 2. But now here's where we're going to start with inequalities. Notice these values of k are exactly the starting values of k to be inside of b sub n. So we're going to replace this with an inequality, and instead of summing through all of these, we'll just sum through the ones that are inside of b sub n. And we know that we'll get something necessarily smaller because there was more restrictions on things inside of b sub n. But now let's expand out for a little bit of exploration on the terms within this sum. Okay, great. So notice that since k is inside of b sub n, we know some things about k. So first of all, k comes from the following set, or it's between the following two numbers, 2 to the n minus 1 and 2 to the power n all minus 1. So that's one fact that we know. Another fact that we know is that sine of k, if we take its absolute value, is less than 1 over n. Those were the two conditions for being inside of b. Okay, well now let's take the reciprocal of k, and notice that's going to flip the inequalities here. So we have 1 over k will be less than or equal to 1 over 2 to the n minus 1, but yet bigger than or equal to 1 over 2 to the n all minus 1. But then by this inequality, we know that k to the power absolute value of sine of k will be less than k to the power 1 over n. But then taking the reciprocal of that, we know that 1 over k to the absolute value of sine of k will be bigger than 1 over k to the 1 over n. But now putting all this together, we're able to bound this below quite nicely. So this is going to be bigger than or equal to s sub 6 plus the limit as our capital N goes to infinity. And then we have the sum as lowercase n goes from 7 to capital N. And then we can wrap all of these together with the smallest possible value of 1 over k, as well as the smallest possible value of this 1 over k to the 1 over n. And then we can replace all of these terms within the k sum with the smallest term. Notice the smallest 1 over k term is given by this 1 over 2 to the n minus 1. And then similarly, you can calculate with this the smallest 1 over k to the 1 over n term. But that means we're adding the smallest term up, the size of b sub n. So here we've got the cardinality of b sub n over 2 to the n plus 1. But now we can replace this cardinality of b sub n with this difference of cardinalities of the a sub n's, keeping in mind that we're going in the same direction from the inequality. So let's just sneak that in here. So we'll have cardinality of a sub n minus cardinality of a sub n minus 1, and we don't really need to worry about it because it goes in the correct direction of the inequality. Okay, so now I'm going to split this up a little bit. So this will be equal to s sub 6 plus our limit as n goes to infinity of the sum as lowercase n goes from 7 up to capital N of the following. So we'll have 2 modulus of a sub n over 2 to the n plus 2. So that's just multiplying and dividing both of these by 2. And then minus size of a n minus 1 over 2 to the n plus 1. But now if you look closely, this term and this term are very similar up to reindexing. So maybe we'll skip this step because we do it on the channel a lot, but you could split this into 2 sums, reindex them, and get some cancellation. And then after throwing away some stuff that you know is positive, you have that all of this is bigger than or equal to s sub 6 minus, well, the terms left over from here, so that would be the size of a sub 6 over 2 to the power 8. So again, that's the term that's left over from subtracting that off. And then plus the limit as our capital N goes to infinity of the sum of lowercase n going from 7 to capital N of whatever's left over. And what's left over will be the size of a sub n over 2 to the n plus 2. So notice we subtracted one of them off from this term right here. That's why we don't have this 2 in the numerator anymore. Okay, so now let's maybe have the inequality that starts here and ends here and work from there. Okay, so here's where we left off, and we've only got a couple of steps left. So now we'll use the fact that a sub n is bigger than this 2 to the n over 7n and see where that leaves us. So here we've got this is bigger than or equal to s sub 6 minus the size of a sub 6 over 2 to the 8, and then plus, well, now I'm just going to write this as the sum as lowercase n goes from 7 up to infinity, applying that limit of, well, I'm going to replace this modulus or this size of a sub n with 2 to the n over 7 times n, and then we've got all of that over 2 to the n plus 2. Notice I had my inequality working, so that's why I was able to make that replacement. Okay, but now let's rewrite this. So this is s sub 6 minus the size of a sub 6 over 2 to the 8 plus, well, notice a lot cancels here. And in fact, in the end, we're left with a 1 over 28 from the 7 and then the 4 that's left over from the powers of 2. And then we have the sum as lowercase n goes from 7 up to infinity of 1 over n. But this thing kind of obviously diverges because it's the harmonic series. And the harmonic series obviously diverges, and it diverges infinitely. So I'll just say that this is equal to infinity. Oh, but notice that our sum is bigger than or equal to this sum. So that means that our sum must also diverge. So that would be like our answer here. Does this thing converge or diverge? It diverges. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.